Hello. Let's assume that at some point you've been asked to add the numbers 1 plus 2 plus 4 plus 8 plus 16 and so on, the powers of 2, right? So how do you do it? Well, this is something called a geometric series, which you can see up here. The geometric series is generally represented by two numbers, which are a and r. In this case, a, which is our initial number, so a is equal to 1, and we have r, which is the number that keeps multiplying the previous term. So we can see that this has been multiplied by 2, this has been multiplied by 2, this has been multiplied by 2, and so on. So r is equal to 2. So in a series like this, we can write the sum as being this: a r to the power of 0. Now mind you, r to the power of 0 simply means 1, so this is just a, plus we have our a to the power of 0 times r, so we're multiplying by 2 now, and this becomes ar, plus, well, the same thing, so we have 0r times r, which is ar squared, and so on up to ar cubed, ar to the power of 4, and so on. So let's rewrite this a bit more neatly. So we have s is equal to a plus ar squared all the way up to ar to the power of n minus 1. If you're wondering why I stopped here, it's because if we count the terms, right, all the terms, we then have n terms in total, right? We have n terms in total if we stop here. Now, to find out what s is, we can multiply s by r, simply writing it as this. We have ar squared, ar cubed, plus all the numbers up to ar to the power of n. Now I'll do something interesting. If you haven't seen this before, you'll find it a bit strange, but I will shift the numbers just visually to the side here. I'll just shift them here, and what I'm going to do now is subtract s, or subtract rs from s. So we have s minus rs is equal to a minus, well, there's nothing here, and we can just write a 0, so a minus 0 is a, ar minus ar cancels out, this also cancels out, these will also cancel out because this should be ar cubed, and this should be ar n to the power of minus 1, which also cancels out, and we can write a 0 here because it doesn't change the sum, and we have 0 minus ar to the power of n, so we have a r to the power of n here. If we factorize, we have that s 1 minus multiplied by 1 minus r, a is then multiplied by 1 minus r to the power of n, and this gives us the general formula: s is equal to a 1 minus r to the power of n divided by 1 minus r. And if we want to find out what the initial sum to this was, we need to just know how many terms we want to sum up, considering this as being the first term, and just substitute into this equation. It's obviously nice to remember formulas, but it's also cool and also important in many aspects to understand how these formulas are derived, as they help you to derive more formulas. So something interesting happens when we have that r is smaller than 1. When r is equal to 1, we know that the sum is just n times a, because a just doesn't change. When r is greater than 1, the series, well, just goes up and up without ever stopping. But at r smaller than 1, something interesting happens, because if you know the property, we have that, say for example, we have 0.9 times 0.9. These are both numbers smaller than 1, and if you multiply them together, you get 0.8 81, right? Same thing happens here. Say you have 0. Say you have 0.5 times 0.5, that's 0.25. The result is always smaller than the initial values. The same applies if you keep multiplying, so like this, right? So you have 0.125, yep, 0.125. So it just keeps getting smaller and smaller. So if you gather this, then you can see that if you have an infinite number of these multiplications, namely r, ar to the power of n, if you have an infinite number of these, right? So you have, we write it formally as this, n goes to infinity, and r is also for r smaller than 1. I will put a modulus here because it doesn't matter if r is positive or negative, as long as it's smaller than 1. So between -1 and 1, this applies. We can see that this actually tends to 0. This is because the terms becomes so small after an infinite number of multiplications that it just disappears virtually. So in the end, if you're summing up an infinite number of terms and you have 0, and your r is smaller than 1, then you get this result here. So looking here, you can see that this part here disappears. So at the top we only have a and 1 minus r. You must have seen an example, well, not must, you probably have seen it, an example where a is equal to 1 and r is equal to 0.5. Probably not in this form. You probably have seen a graph going like this. So you have a cube of 1 by 1. You then add a half to it. Then you add a quarter to it. Quarter of a cube. That does not look like a half, does it? Nope. Maybe here. And you add a quarter. Then you add an eighth. And so on. So oops. And so on. This continues. So what we can see here is something interesting. It starts to converge, and that's what it's doing here. This applies because the series here is converging. So if we write if we substitute these two values in the formula, we get that s is equal to a, which is 1 minus 0.5, and we can use this formula because r is less than 1, and you can see that the total area is 2. Wow. The reason why I say area is because I use the graph here to show that this indeed happens. I don't expect this to happen for all combinations of numbers. This is just a nice visual example as to why this happens. Well, the major outcome of this video should be how to derive these two particular formulas for the geometric series. And the two different, so this always works, and this works in the case where the modulus of r is less than 1 and you have an infinite number of terms, which does happens every now and then. I hope you found this video useful, and yeah, no, thank you for watching.